Dear students, I am Dr. N. Prabhavati, Head and Associate Professor, PG and Research Department of Physics, Sri Sharda College for Women, Autonomous, Salem 16. In this video, I am going to give a brief idea on electrostatics. The branch of electricity which deals with stationary charges is called electrostatics. Stationary charges means the charges which are at rest. Let us see the definition for electric charge. Electric charge is a physical property of matter that causes it to experience a force when close to other electrically charged matter. The SI unit of charge is coulomb. The charge on an electron is minus E. The charge on the proton is plus E. The magnitude of E is given as 1.6 into 10 to the power of minus 19 coulomb. The charge on electron and proton is the same in magnitude, but they differ only in the sign. Where is the charge? The charge is in atoms. We know that the atom is electrically neutral and is made up of the negatively charged electrons, positively charged protons and neutrons that have zero charge. So, the charge is in atom. And also we came to know that protons are having positive charge and electrons are negatively charged. We already know that matter or the material object is made up of atoms or neutral in general. That means it has the same amount of positive and negative charge. Generally, electrons can be transferred from one object to another by rubbing. Charging the object through rubbing is called triboelectric charging. Triboelectric charging. When the glass rod is rubbed with silk cloth, negative charges are transferred from glass rod to silk cloth. As a result, the glass rod is positively charged and the silk cloth becomes negatively charged. Whereas, when the rubber rod is rubbed with fur, negative charges are transferred from fur to rubber rod. As a result, the rubber rod is negatively charged and the fur becomes positively charged. It leads to the conclusion that charges are neither created nor destroyed but can only be transferred from one object to other. This is called conservation of total charges. Basic properties of electric charges. The very basic nature of electric charges are like charges repel each other, unlike charges attract each other. The second property, the charge is a scalar. The third property is conservation of charges. That means the total electric charge in the universe is constant. You can also say that charge can neither be created nor be destroyed. That means in any physical process, the net change in charge will always be zero. The fourth property, quantization of electric charge. The charge Q on any object is equal to an integral multiple of E. Hence, Q is equal to NE. Here, N is any integer and E is the fundamental unit of charge. When a glass rod is rubbed with silk cloth, the number of charges transferred from glass rod to cloth is usually very large, which is of the order of 10 to the power of plus 10. We know that Q is equal to N into E. The E is the order of 10 to the power of minus 19 and N is the order of 10 to the power of plus 10. Therefore, is the order of 10 to the power of minus 9. So, the charge quantization is not appreciable at macroscopic level. Hence, the charges are treated to be continuous, not discrete. This is called quantization of charge. Coulomb's law: force between two point charges kept in vacuum or free space can be obtained with the help of Coulomb's law. Here in the figure, Q1 and Q2 are the 2-point charges kept in vacuum or free space. These 2-point charges are separated by a distance r, where this r12 cap is nothing but a unit vector pointing from charge Q1 to Q2. F21 is the force on the charge Q2 exerted by Q1, which is acting along R12. Therefore, according to Coulomb's law, the force F21 is equal to K into Q1 Q2 divided by R squared into R12 cap. This R12 cap is nothing but a unit vector, and K is the proportionality constant. Q1 and Q2 are the point charges. R is the distance between the 2-point charge, where K is given by 1 divided by 4 pi epsilon naught. The numerical value of which is 9 into 10 to the power of 9 Newton meter squared per Coulomb squared. We should also note that the force F12. What is force F12? Which is nothing but a force on the charge Q1 exerted by Q2 is along minus R12. That is, the direction is opposite to R12, because F21 is the force on the charge Q2 exerted by Q1, whereas F12 is the force on the charge Q1 exerted by Q2. Therefore, F21 and F12 are in opposite direction. Force between two stationary point charges kept in a medium of permittivity epsilon is given as F12 equal to 1 divided by 4 pi epsilon multiplied by Q1 Q2 divided by R squared multiplied by the unit vector R12 cap. Here, this epsilon is nothing but the permittivity of the medium. This permittivity of the medium epsilon is always greater than the permittivity of free space epsilon naught. Therefore, the force between 2-point charges in a medium is always less than that in vacuum. Next, the relative permittivity for a given medium. The relative permittivity for a given medium is represented as epsilon r, which is nothing but the ratio between the permittivity of the medium to the permittivity of free space. Therefore, epsilon r is equal to epsilon divided by epsilon naught. We know that epsilon is always greater than epsilon naught. Therefore, epsilon r is always greater than 1 for all the media except the air or in vacuum. Therefore, the relative permittivity for a given medium is always greater than 1, but for air or vacuum, the relative permittivity eta r is equal to 1. Important aspects of Coulomb's law. Coulomb's law states that the electrostatic force directly proportional to the product of the magnitude of 2-point charges Q1 and Q2 and then inversely proportional to square of the distance between the 2-point charges, and always lies along the line joining the 2-point charges, that is along the direction R12, that is from Q1 to Q2. The permittivity of free space or vacuum, epsilon naught. This can be determined from the equation k equal to 1 divided by 4 pi epsilon naught, where k is nothing but the proportionality constant and its value is equal to 9 into 10 to the power of 9 Newton meter square per Coulomb square. Therefore, from the equation k equal to 1 divided by 4 pi epsilon naught, the epsilon naught is found to be equal to 1 divided by 4 pi k. Here if you substitute for k, the value of epsilon naught is equal to 8.85 into 10 to the power of minus 12 Coulomb squared per Newton per meter squared. Next we are going to calculate the magnitude of the electrostatic force. The magnitude of the electrostatic force between the 2-point charges, each of 1 coulomb and separated by a distance of 1 meter. According to the Coulomb's law, the force F is equal to K into Q1 Q2 divided by R squared multiplied by the unit vector R1 to kappa. Here we are going to substitute K, that is equal to 1 divided by 4 pi epsilon naught. The value of 1 divided by 4 pi epsilon naught is nothing but 9 into 10 to the power of 9 Newton meter squared per Coulomb squared. Substitute this value for 1 divided by 4 pi epsilon naught. And Q1, Q2 are nothing but 1 coulomb. And these two charges separated by a distance of 1 meter. Therefore, R is equal to 1. Therefore, R squared is 1 squared. Then if you evaluate this is equal to 9 into 10 to the power of 9 Newton. Here you must notice that this is a huge quantity, almost equal to weight of 1 million ton. In practice, we never come across 1 coulomb of charge because most of the electrical phenomena in day-to-day life involve electrical charges of the order of 1 microcoulomb or nanocoulombs. The next aspect is Coulomb's law has same structure as Newton's law of gravitation. According to Coulomb's law, electrostatic force between two charges is equal to K into Q1 Q2 divided by R squared. According to Newton's law of gravitation, gravitational force between two masses is equal to G into m1 m2 divided by R squared. From this equation, we can infer that both the forces, that is electrostatic force as well as gravitational force, are inversely proportional to the square of the distance between the two particles. And electrostatic force is directly proportional to the product of the magnitude of 2-point charges, whereas the gravitational force is directly proportional to the product of two masses. The next one is electrostatic force can be attractive or repulsive depending on the nature of the charges, whereas gravitational force is always attractive. The third point is electrostatic force depends on the nature of the medium in which the 2-point charges are kept. Gravitational force is independent of the medium. According to Coulomb's law, the value of K is equal to 9 into 10 to the power of 9 Newton meter squared per Coulomb squared. Here K is greater than G G is the gravitational constant. Therefore, electrostatic force is the stronger one compared to gravitational force. That is, the electrostatic force is always greater in magnitude than gravitational force. According to Newton's law of gravitation, where G is equal to 6.67 into 10 to the power of minus 11 Newton meter squared per kilogram squared. The value of G is less than K, therefore gravitational force is a weaker force compared to electrostatic force. Seventh aspect, we are going to show that electrostatic force obeys Newton's third law. According to Coulomb's law, the force on a charge Q1 exerted by the point charge Q2 is given by F12 is equal to 1 divided by 4 pi epsilon naught Q1 Q2 by R squared multiplied by the unit vector R12 with negative sign. Here we are considering the negative sign because the force F12 always acts in a direction opposite to the direction of unit vector R12. Therefore, F12 is now equal to minus 1 divided by 4 pi epsilon naught Q1 Q2 divided by R squared multiplied by the unit vector R12. The quantities in the right hand side, that is 1 divided by 4 pi epsilon naught Q1 Q2 divided by R squared, the unit vector R12. This is nothing but the force F21. Therefore, F12 is equal to minus F21. From this, we came to know that the force F12 and force F21 are equal in magnitude but opposite in direction. Thus, we proved that the electrostatic force obeys Newton's third law. The last one is, we know that the expression for Coulomb force is true only for point charges. But the point charge is an ideal concept. However, we can apply Coulomb's law for two charged particles whose size are very much smaller than the distance between them, because the distance between the two objects are very much greater than the size of the object. Therefore, you can treat any object as a point charge and you can apply this Coulomb's law for any two objects. The next important principle in electrostatics is superposition principle. We all know that Coulomb's law explains the interaction between two point charges, whereas this superposition principle explains the interaction between multiple charges. According to this principle, the total force acting on a given charge is equal to the vector sum of forces exerted on it by all the other charges. Let us now consider a system of n charges, namely Q1, Q2, Q3 up to Qn. From Coulomb's law, the force on Q1 exerted by the charge Q2 is F12, which is equal to K into Q1 Q2 divided by R21 the whole square multiplied by the unit vector R21. The force on Q1 exerted by the charge Q3 is F13, which is equal to K into Q1 Q3 divided by R31 the whole square multiplied by the unit vector R31. By continuing this, the total force acting on the charge Q1 due to all the charges is F total, F1 total. Why it is F1 total? The force acting on the charge Q1. Therefore, F1 total, which is equal to the sum of F12, F13, F14 up to F1n. Therefore, F1 total is equal to this one. That is, here you have done this expression by substituting for F12, F13, F14 and also up to F1n. Like this you get this expression. Both this superposition principle and Coulomb's law form fundamental principles of electrostatics and explains all the phenomena in electrostatics. Thank you.